In this video, we're going to review the main topics that we discussed in the pre-algebra chapter of the algebra textbook, chapter R. Okay, so when we started, one of the things that I wanted to do was, from the very beginning of this course, I thought it would be really helpful to go ahead and introduce you to the existence of complex numbers or imaginary numbers. So we didn't go into much detail at all on what complex numbers are or like why they were invented. I just wanted to make you aware that they exist, okay? And so the idea was that, so all throughout, grade school, elementary school, all of the addition, subtraction, all of the math that you learned outside of geometry, like shapes and whatnot, so math with numbers, was we were working with any number on the real number line. So you can graphically think about all numbers that we had worked with before, coming into algebra as existing on a line like this, because it extends infinitely in both directions, in the positive and negative directions. So you could have like a really enormous positive number, right? A trillion. But it can go, but it goes as big as you can possibly imagine, but same in the negative direction, right? But even going from like just between 0 and 1, there's an infinite number of values, like 0.583, a trillion zeros, 523, etc. So you can think about all numbers that we could possibly choose from would be on this number line here, called the real number line. And these are called real numbers. Okay, and we talked about how we could separate these real numbers into different categories. And a math term that we use for if we're putting something into a group or a category is a set. So you have sets of not just numbers, but whatever you want. It's something you want to kind of put into its own box, and so you can compare that to something else or just whatever. That's the idea of a set. So a set is made up of elements. And you could list out the different elements, or if there's an infinite number of elements, like the set of real numbers, then you can't really list them out. But still, okay. Now these elements in a set, so like you could have the set of the numbers 1, -2, 5. That's a set. A set is just whatever you want to separate. It's made up of these elements that you want to put into a group to compare to other sets or whatever. But it's made up of it can be made up of numbers, but it can be made up of it's called being made up of elements because it's not just numbers. Like in geometry, we can make sets of different shapes, like a set of triangles or a set of polygons, right? But then there's also, you can think about something as being a subset of a set in the sense that, so we visualize sets. One way we do this is with like these Venn diagrams. So if you have the set of all polygons, okay, that's set A. You can represent a set with a letter. I'll call that set P. You can represent a set with a letter. Well, then the set of all triangles, since every triangle is a polygon, is a subset of polygons. So you draw it like this, okay? And so what we did was we took the set of all real numbers and broke it down completely into these different subsets. So where you could take all real numbers and break them down into separate subsets. And so we looked at the natural numbers, the whole numbers, the integers, the rational numbers, the irrational numbers. And it was the case that, so you take all real numbers, these are all real numbers, this entire number line, and you could have its own group. Over here was the irrational numbers, and then over here was the rational numbers. And then, but subsets of the rational numbers were the integers and the whole numbers and the natural numbers, which were like subsets of each other. So every natural number is a whole number. Every integer or every whole number is an integer. Every integer is a rational number. But then irrational numbers are in their own group. And then all that together, it's like that's all real numbers. Okay, but if we take this real number line here and we add, so I'm going to remove this R here because now we're going to talk about the set of complex numbers. And if we add an axis here, So now we go from having just a line to this entire plane. Okay, but the set of all real numbers are contained within this plane here. We just don't put this because it's a new set. Okay, this is the set of all complex numbers. Now you can pick any point in this plane, and that's going to be a number. That's what we're going to be working with in algebra and really all applied mathematics for engineers, mathematicians, etc. We're not going to go any farther past the complex plane. We're going to deal with this complex plane of numbers. But if you just stay on the horizontal axis, then you've got a real number. And the whole idea is if you have another axis like this, then it's like two-dimensional in the sense that, like if you had y and x, you need these two separate dimensions, because if you have something like 3x minus 2y, well, you can't combine this anymore. This is fully simplified. As opposed to if you have two separate real numbers are one-dimensional, so 3 plus 2, well, you can simplify this further to just one dimension, one value, one parameter. But it's the idea is we're going to have this new number called an imaginary number, I. And so now if you're in any point in this complex plane, the idea is you go like this number here. If this was minus 1, minus 2, minus 3, if you went 2 minus 3, that means you're going to be, this is a complex number, 2 minus 3i. And it's two-dimensional, so you can't combine these any further. And that's why when it comes to complex numbers, you have this entire plane of numbers to choose from. With real numbers, you have this entire line to choose from. Now with the complex plane, you can still stay on that line and choose any natural number, whole number, integer, etc. Or you can move off that line and choose any complex number in this entire plane that you want. And so that's now, but what exactly does I mean? Why do we need these numbers? We're not getting into that right now. We'll get into that later. But the idea is now we have this entire plane of numbers to choose from, as opposed to just this line of numbers. And since we're in a plane, that means it's two-dimensional, meaning that a number is gonna be like you can't simplify it. You have to have two separate, distinct parameters. That's what that two-dimensional means. You can't specify a point in 3D space without these three distinct values, as opposed to like time is, from my perspective, or temperature is one-dimensional. You just need one parameter to describe a time, the time that something is, or the temperature that something is. The only thing, at least from our perspective right now, we only see time and temperature through one dimension. But 3D space, you have to have three separate dimensions. But we're sticking into a plane here, so it's just two dimensions. Okay, so now, when it comes to sets, so a set is you can make a set to be anything you want. You define a set, but you can perform operations on sets in the sense that, like, to create new sets. So there's only two operations here that we talk about. So you can do, if you've got a set A of certain elements, right? And this is a set A. It's made up of all these elements. Okay, and another set B, then you can think about you could say, okay, I'm going to define this new set C, that's the union between set A and set B, and you symbolize it this way. What that means is that you're going to take everything from set A and everything from set B and put them all into one set, but without duplicates. So if there's the same, if you have the same element in set A and set B, you just take that one time. But it's everything in set A and everything in set B. So even if they're, they show these examples here where they're the general Venn diagram where there's some overlap between the sets, right? You have some elements that are in both set A and set B, some elements that are just in set A and just in set B, but you're taking everything from both sets. Even if they were separate, you're taking everything from both sets and making this new set C, but with no duplicates. Okay, now you could make also, and that would be this new set C. Now you could also make a new set where you do the intersection of sets A and set B. And that just means you only take what's in both set A and set B. without duplicates, right? If it's in both set A and set B, then you put it into this new set. Okay. Then we talked about the idea of the absolute value of a number and then how we represent that in variable form. Okay, but we looked at this from the perspective strictly of real numbers. So the idea is when you talk about the absolute value of a number, you're asking how far is that number from zero, just in magnitude. Like there's no negative here. It's just if you have a number here, -2, or a number here, 5, what's this distance? That would be the absolute value of 2. Or what's this distance? That would be the absolute value of 5. It has nothing to do with a sign. It's just like the magnitude of its distance from 0. And you can also think about that. We're going to learn later. We're not going to talk about this in algebra, but what would be the parallel for the absolute value of a complex number? Well, it's distance from 0, right? You would think. We'll talk about that later, but it would be this, perhaps. That's interesting to think about. Okay, but we didn't talk about that. We stuck with the real numbers. And so if you're going to do this in variable forms, like the definition of the absolute value, the way you look at this is the absolute value of x is such that if x is greater than or equal to 0, then it's just whatever x is. But if x is less than 0, then it's minus x. Because it's like, if x is -2, then you want to return the absolute value, well, you need to multiply -2 by -1 to get 2, right? If x is 7 or 0, well, then you don't need to do anything. Just that's it. Okay? Now, we also looked at how the absolute value could be used to determine the distance between two numbers on the number line. So this distance here. And that distance, you could say, is equal to the absolute value of b minus a, or equivalently, the absolute value of a minus b. Okay, and now a parallel to that with complex numbers is interesting to think about. In the sense that, so what would be the distance between these two complex numbers, the straight line distance? It's interesting. Could we use an absolute value of a complex number to do that? We have to think about it. Okay, then we looked at these fundamental properties of numbers: the commutative property, associative property, identity property, distributive property. And these are actually really important. And it's a big deal that, like, if you're going to call something a number, the fact that we call any complex number in the entire complex plane a number, okay, it's a big deal when we say that. And you can think about the meaning of if you're going to be called a number, something's going to be called a number, it has to obey these properties here. And yes, any number in the entire complex plane obeys these properties. Now, you might be saying, well, what's the big deal? I mean, these are just like really fundamental properties. These are, like elementary properties. I mean, what about properties that include some of the more advanced stuff that we've been learning, right? Exponents, rational expressions, et cetera, et cetera. Well, no, these are much more comprehensive than you realize. It specifies the basics of what we do when we add, subtract, multiply, divide, and even distribute, right? It specifies the basics of the fact that, so if you have two complex numbers, 3 minus 2i over 5 plus 2, or no, over 3 minus 2i, okay? Well, since this obeys the properties of numbers, this is equal to 1. Similarly, if you have 0 times a complex number, that equals 0. And that's one of the reasons we talked about in how if you're going to try and define dividing by 0, so some number divided by 0, and you're going to say that's some new number, the wizard number. Well, if you're going to do that, then 0 times the wizard number needs to be equal to not be equal to 0. Well, that's not how numbers behave as far as how they're defined, right? Any number you're going to invent needs to obey these properties, and that's what imaginary numbers do. Every number in the complex plane obeys these properties. And again, so you still might be saying, well, why are these seem so elementary? Well, no. So everything that we've So you have addition, subtraction, multiplication, division. But what is like x squared or x to the power n, some integer exponent? Well, that's just multiplication, just in this packaged form. Same thing with a negative integer, but it just incorporates division into it. It's division with multiplication in the denominator. What's a radical? Right? A rational exponent power. That's just the opposite of a power. It's the opposite process. In the same way that division is the opposite of multiplication, it's just like if you take the nth root of x to the n, you get x. When we get to exponentials and logarithms, that's just a number to the power x. That's just multiplication. Logarithms are the opposite of this. So it's a really big deal if that we can say that complex numbers obey these fundamental properties of numbers, as well as real numbers, obviously. I mean, this is the heart and soul of everything we do in all of algebra. Commutative property, associative property, the identity property, the fact that if you add something to its opposite, you get 0. Well, that's how complex numbers work, 100%. 3 plus 2i, if I add that to its opposite, minus 3 minus 2i, that's going to be 0. Okay, so then next, we looked at integer exponents. So this was, we had already talked, coming into pre-algebra, we already had a sense for what something like 5 to the third power meant. A number to any number to a positive integer exponent was just repeated multiplication that many times, right? Even if this was negative, that's no problem. So minus 2 to the fourth is just minus 2 times minus 2 times minus 2 times minus 2. That would be positive 16. Okay? But then we wanted to think about what it meant we wanted to extend this definition. This you have a number, a base to a positive integer exponent. We wanted to extend that definition to negative integers and 0. And we saw that, so so you had b to the first, b squared, b cubed, etc. We saw that you multiply by b each time to keep going up. But if you go in the other direction, you're dividing by b. And so we could see that if we continued this pattern, b to the 0, b to the minus 1, b to the minus 2, then you could a very simple extension to the b to the n, to a positive integer exponent, was that, so any number to the power 0 would be 1, except for the base can't be 0. And then any number to a negative integer exponent would be 1 over, would be this. Except for the case if this is universally true, except if the base is 0, then there is no 0 to the 0 or 0 to a negative integer. That's undefined. But everything else works just like this. Okay, next we wanted to continue to extend this, the meaning of a number to a different kinds of powers for the case of, so we had just defined it for all integers, b to any integer, positive or negative. But what about b to a rational exponent? Like b to the 2/3, some number to the 2/3, for example. What would that mean? Well, first we needed to be clear on exactly what a radical means, the radical symbol, which is like the inverse of exponents. We had to be very clear on what the nth root of a meant. Okay, and the whole idea was that this needs to be clearly defined. This needed to be clearly defined because when it came to the opposite of powers, the idea was that you're saying that if you have a power like 5 squared, that's 25. Well, what if you want to go in the other direction and you're given 25 and you want to figure out, okay, well, what number when I take it to some power do I get 25, right? Well, this was the first time, as far as we had done addition, subtraction, multiplication, division, this was the first time where there was some ambiguity, in the sense that if you're going this hadn't happened before with any of the operations we had worked with so far, and that there was some ambiguity, because if you're going to ask a question like, what number, when I take it to the second power, do I get 25? What real number? What of all the different real numbers I can choose from, which one or ones, when I take it to the second power, do I get 25? Well, based on the definition of multiplication, there was 2 of those. 5 squared is 25, and minus 5 squared is 25. And so because of that ambiguity, there needed to be this root operation, the opposite of exponents, that had some restrictions placed on it, because you don't want to be working with equations and have some operation that has two possibilities coming out of it. That could be very confusing and problematic. You want to be able to say, okay, look, for any given operation that I'm doing in math, I'm solving a problem, I don't want to have, just these, in general, these two possible values come out of it. So that was the whole point of the principal root, this radical symbol, the principal nth root of a. Across the board, there's going to be one value that's going to come out of this, one value. And so we talked about the exact definition of the meaning of a radical. Okay? And so then with that, to define what be a number to a rational exponent meant, we used the properties of exponents. So like the fact that if you have a to the m to the n power, that's a to the m times n. Or if you have a to the m times a to the n, that's a to the m plus n. Those different properties. If you have let's see, what else? There was, if you have a times b to the power m, that's a to the m times b to the m. Those different properties. We use those properties to define what exactly this meant. And it made perfect sense that this means you have either b, the principal nth root of b to the m, or equivalently, you have the principal nth root of b, all of that to the m. And that was it made perfect sense to define it this way. Okay, and so now all that's left, we didn't do this in this chapter, is so what about an irrational exponent? That's the only remaining real number we haven't thought about what a number to an irrational exponent would mean. Okay? So, but then from there, now that we had officially defined radicals, we looked at some different properties of radicals. For example, if you have the principal nth root of a times the principal nth root of b, then you can write that as the principal nth root of a times b. Or there's a nested radical in the sense that if you have the principal nth root of a and then the principal mth root of all of that, then you can simplify that as the principal m times nth root of a. Okay, but now there was one of these properties was a little bit tricky. It was the fact that if you have a to the power n, and then the principal nth root of this, but n is even. If n is even, well then, okay, based on the definition of rational exponents, you could write this as a to the n over n. A to the n over, so n over n is 1, you get a. However, this is not correct, because if you had, for example, if a was minus 5 and n was 2, well, this is not equal to minus 5, this is equal to 5. So you needed to say that this was equal to the absolute value of a. And this property was a little bit confusing in terms of, okay, so we worked a bunch of examples on simplifying radicals. And so how do you make sure you account for this taking out an absolute value? And so that was a bit tricky, and we talked about that extensively, as well as, well, okay, then, well, what would this mean? Minus, if you started with this, well, okay, that's, if we started with this, minus 5 to the first, minus 5, well, that's not the absolute value of minus 5. So this was a little bit tricky, but we went through this in detail in the textbook and then in the example problems as well, to make it very clear on how to simplify if you're having to use this property with this. It's like the principal nth root of a to the n power if n is even. Okay, next we were introduced to polynomials. Okay, and what we talked about was that in all of algebra, one of the things that we're going to be doing is putting different types of expressions into variable expressions into these categories. And when we talked about that, it's not nearly as intimidating or like hard to memorize and understand as you think it is. It seems like it is when you're first going through algebra, but it's not nearly as intimidating as you think. In particular because, so what makes two expressions different has nothing to do with how you're adding them, like, whether or not you're adding, subtracting, or multiplying or dividing. So categorizing an expression has nothing to do with addition, subtraction, multiplication, division. It's just about the types of variable terms you have in terms of the operations that are being applied to the variables. Well, okay, in all of algebra, we have like a variable to a positive integer power, 2x to the 5th, okay? Or you could have a variable that would include x to the 0, that's just a constant. Or you could have x to like a negative integer power. Or you could have like x to a rational exponent, and that includes radicals, right? And then what we're not going to talk about right now to an irrational exponent. But then this is it. This is it. This is it right here. In all of algebra, these are the only kind of operations to variables that we use. And you might think, well, what about exponentials and logarithms? Those are just functions. That's just a certain type of function in the sense that this b to the x is taking in all of these and putting it into one function. This is just a power. And again, the log is the opposite of this. So the different categories that we have is just based really on this here. And then if you have an exponential or a logarithm, then that's another kind of category. But it's really not nearly as much to keep track of as you think it is. Okay, so then we learned about, we talked about multiplying radical expressions and multiplying polynomial expressions and simplifying, adding, subtracting, simplifying these different types of expressions. Okay, we developed these formulas here to where if you have like a plus b times a minus b, then that's a special case product. But the idea was that a and b could be any kind of variable expression. How we simplify polynomial and radical expressions and add, subtract them, those are all just numbers. That's any kind of number from the entire complex plane. That's what a variable can be a placeholder for. Any variable expression you can think about in general can be a placeholder for any number in the entire complex plane. So you can, if we're going to develop a formula like what's a plus b times a minus b, that's just addition, subtraction, multiplication, division, distributing, right? So all of these formulas you can apply with any kind of number you want. It applies across the board, radicals, whatever. We're just dealing with numbers here. So we looked at these special case products, like if a could be any variable expression, b could be any other variable expression, right? If you got, and this could be, or you could have radicals, whatever. If you have and these are just placeholders for numbers in the entire complex plane. If you do a plus b times a minus b, you're going to get a squared minus b squared. There's difference of squares. And then if you do a plus b squared or a minus b squared, you get this form here, which if you're dealing with a polynomial, it's a perfect square. It's called a perfect square trinomial. When you're using these variables here, like a and b as placeholders for actual other expressions, then you get this perfect, well, this is a difference of squares binomial. But if you're just doing like a plus b squared, you get a perfect square trinomial, or a minus b squared. Okay, then we talked about factoring. Factoring is really about polynomials. This is dealing with polynomials. You're taking any polynomial expression. Okay, so a polynomial expression is, some coefficient times x to the 5th. It's all x to some whole number exponent, 1, 2, 3, 4, 5, or even x to the 0, but that's just a constant. So it's been all, you have a polynomial expression that's expanded out and just it's all expanded out, no brackets or anything, and you want to turn that into a product of factors. In the same way that so it's similar to if you have something like 36. Well, we can break this down into a product of factors. Right? And it's a similar idea as far as what you're doing with polynomials. You're taking a polynomial, you're starting off with x cubed minus 3x squared plus 5x minus 1, and you're turning that into this product of factors. So we went into detail on the different methods you can use to factor different kinds of polynomials, binomials, trinomials, etc. Now, we saw that there's, after this, we got through this section, there's still a lot more polynomials, a lot of polynomials that we weren't able to factor. However, just note that when we get to chapter 3, we're going to learn some extremely powerful techniques that will allow us to factor any polynomial, no matter what it is. Okay, now the last section was on rational expressions, and we talked about some more operations on radicals. So we were just learning how to multiply and add, subtract different kinds of radical expressions, polynomial expressions, etc. But that's all associative, commutative, distributive properties. But we just looked at we looked at each of these types of expressions individually because there's subtle nuances here and there that make them slightly different. But it's all just, again, it's all just distribution, adding like terms, etc. Okay, but we looked at rational expressions. This was a new type of category of expression. With polynomials, you were dealing with x to these whole number powers, or not even just x. Even it could be multiple variables as well. You can have a polynomial expression and multiple variables. You're just dealing with these whole number powers. Okay. With a rational expression, you're dealing with negative integer powers. Or another way of looking at this is you've got variables in denominators that are raised to whole number powers. So no radicals. No radicals. Variables in denominators raised to whole number powers, those are rational expressions. Now, that's an informal definition. The more technically correct math definition of a rational expression is that it's a ratio of polynomials. But I like the informal definition for the case of people that are just using a non-math majors, because if with the formal definition, then even like a linear expression, this is also a rational expression because, okay, 3x plus 1, okay, the technical definition of a rational expression is to where every single term is rational. Well, yeah, this is a ratio of polynomials. This is a first order polynomial with leading coefficient 3. This is a 0th order polynomial with leading coefficient 1, 0th order polynomial with leading coefficient 2. So these are all ratios of polynomials, right? Well, for non-math majors, to me, that makes it a little bit difficult to keep track of what you're looking at. So an informal definition of a rational expression is you have variables raised to whole numbers in denominators of at least one term. Okay, so then we learned how to do operations with rational expressions: add, subtract, multiply, divide, and then that was it. So those are some of the main topics we talked about in pre-algebra.